as the era of autonomous vehicles comes closer, important questions remain about what it means for an AV to drive safely. To this end, Mobileye has developed the Responsibility-Sensitive Safety Mathematical Model, or RSS, which codifies open, transparent, complete, and verifiable rules. An essential part of developing RSS was the understanding that to balance between cautious and assertive driving, we need to make reasonable worst-case assumptions of what other road users might do. Assumptions set clear boundaries on the most drastic action we can reasonably expect another driver to undertake, which are programmed into the parameters to account for and protect against any behavior by other road users. This is different from predictions. Exactly what will that other car do, which can often prove dangerously wrong. The idea of reasonably foreseeable is important here. We don't reasonably expect the vehicle in front of us to suddenly reverse and back into us. We also don't expect a vehicle in front of us to brake with jet engine levels of deceleration. However, we can envision a scenario where the vehicle ahead suddenly stops with a reasonably foreseeable level of braking. Our AV needs to be prepared for all variations of this foreseeable human behavior. Only then can the AV safely navigate the infinite number of real-world driving scenarios while still driving naturally amongst other human road users. Assumptions like this are at the heart of what it means to drive safely, and RSS allows us to model them. We often get asked how RSS works in real-world driving situations. In this video, we're going to examine the Mobileye AV as it travels the crowded streets of Jerusalem, encountering everyday complex driving situations, and illustrate not only how the 5 rules of RSS can support anything the world throws at our AV, but also share values that can be used to set the reasonable worst-case assumptions that enable machines to drive much safer than humans do, but still be able to navigate alongside other human drivers. Here, we see a typical urban scene. Our vehicle is traveling behind a large truck, in this case, a car carrier. We need to keep a safe distance, prepare for any sudden stops, while still not interfering with the heavy traffic around us. Now let's slow down and closely examine a small section of this drive to see exactly how RSS Rule 1 works. Do not hit someone from behind. RSS provides a minimum safe distance formula, which is a highly accurate calculation of the distance required to avoid hitting the front vehicle from behind. Compare this to the 2-second rule, a crude human estimate on which AVs can significantly improve. Our vehicle knows its own speed and braking capability. RSS accounts for the situation where the automated vehicle may be accelerating within the time it takes to respond to the braking of the vehicle in front. While autonomous systems make decisions in a fraction of the time it takes a human driver, the system still needs to account for some response time. The 360-degree camera-only sensor suite calculates the car carrier's speed and longitudinal distance from our vehicle. Here's the critical part. We must make a reasonable, worst-case assumption about the braking capability of the vehicle ahead. Should it be the braking capability of a race car? Or should we assume a more reasonable braking value? In this case, we've selected -6 meters per second squared, a value that is based on naturalistic driving studies of human drivers. Using these parameters, RSS calculates a minimum following distance such that the AV would be able to avoid a crash if the vehicle in front were to suddenly brake no harder than the assumed reasonable worst-case braking capability. This results in a naturalistic following distance that is provably safe up to the reasonable and foreseeable assumptions. The AV is following at a distance greater than the minimum distance specified by RSS. The AV is applying a jerk-bounded braking profile to provide a more comfortable experience on top of RSS, constantly recalculating the minimum safe distance to ensure it is still driving safely according to RSS, and in doing so, absorbing the natural fluctuations that are common with human drivers. Here, the car carrier has suddenly revealed a stopped car in our lane. The car is classified as an obstacle we need to overtake, and the AV goes around it. For the upcoming maneuver, RSS rule number 2 is needed. Do not cut in recklessly. After passing by the stopped vehicle, the AV is faced with two obstacles: a vehicle pulling out and a motorcycle coming from behind. The AV must evaluate the longitudinal and lateral safe distances with respect to these new vehicles. Let's see how RSS deals with this complex situation. RSS's safe lateral distance formula considers the current lateral velocities of each vehicle. In this case, our lateral speed of 2.5 meters per second means we are moving left to right at that rate. The lateral speed of the white vehicle means it is moving right to left at 1.7 meters per second. We know how much time it takes our AV to respond, and we assume a human driver response time of 1 second for the other vehicle. Mu provides for a small amount of lateral distance variation within the lane, but here again, we need to make an assumption about the minimum lateral braking of the white vehicle. In other words, how fast can it steer away from a lateral conflict? And for this, we assume negative 0.8 meters per second squared. With these parameters, RSS concludes that the lateral distance is unsafe. From a longitudinal standpoint, the AV determines it is following the white vehicle at a distance greater than the minimum safe distance specified by RSS. In RSS, a dangerous situation is when there is a violation of both lateral and longitudinal safe distances. In this case, only the lateral distance is unsafe with respect to the white vehicle. Therefore, the AV understands that it doesn't need to take action. For the motorcycle that is approaching the AV from behind, the longitudinal distance is unsafe, but the lateral distance is still safe, so in neither case do we encounter a dangerous situation. At this point, we again identify an unsafe lateral distance with respect to the white vehicle and an unsafe longitudinal distance with respect to the motorcycle. However, RSS does not identify this as a dangerous situation, since that would require both longitudinal and lateral violations. Sensing a new vehicle up ahead, our concern is that the black vehicle leaving the parking lot might encroach upon our lane and take the right-of-way. Let's take a closer look at how rule number 3 works. Right-of-way is given, not taken. Since the black car remains stopped, our AV intends to navigate around it, maintaining safe distances at all times. All of a sudden, things change. The black vehicle starts accelerating, encroaching into our lane. Based on the assumed response time and braking capability for human drivers, RSS tells us where the black vehicle would be if the driver were to suddenly stop. As that would be in our lane of travel, we use rule number 3 and give way to the other vehicle. Practical driving in the real world does not just mean knowing when to yield, but also when to preserve the right-of-way. In this scenario, RSS will allow the AV to negotiate with other vehicles to safely but assertively navigate an intersection. Here, a black vehicle is coming from the left. RSS rule number 3 requires that the AV continuously ensures that the black vehicle has enough distance to stop without encroaching on the AV's intended path. As long as this is the case, the AV knows it can keep its right-of-way because the black vehicle can still stop in time, using at least the minimum reasonable braking force. Therefore, we assume the black vehicle will follow the rules and yield the right-of-way. This prevents the AV from unnecessarily yielding. Using reasonable worst-case assumptions about other vehicles, we can determine that the black vehicle's current estimated stopping distance will still allow it to stop before encroaching on the AV's lane of travel. The black vehicle continues moving forward, but RSS indicates that it can still stop without encroaching upon the AV's lane of travel. The AV senses another vehicle approaching from the right. It now needs to check that the other vehicle will also respect its right-of-way. Performing RSS rule number 3 calculations, the AV determines that the white van can still stop without encroaching on the AV's lane of travel, and so the AV continues forward, keeping its right-of-way. At this point, the white vehicle has come to a complete stop, letting the AV keep its right-of-way. RSS enables safe but assertive driving, allowing the AV to negotiate with surrounding vehicles and drive through the intersection safely and usefully. The RSS model is more than just safe distances. It also defines proper responses to be performed when encountering dangerous situations. Here we see 2 lanes that merge into one as we approach the roundabout, and a silver vehicle driving close to the automated vehicle to its left. As before, we calculate the safe longitudinal and lateral distances with respect to the silver vehicle. RSS indicates that we are entering into a potentially unsafe situation longitudinally, but not unsafe laterally. Here, something important happens. RSS indicates that both the longitudinal and lateral distances are potentially becoming unsafe, and we should avoid an imminent dangerous situation. Because the lateral distance was the last to be compromised, a lateral proper response must be performed. Just like the longitudinal case, we need to make an assumption about the lateral minimum braking capability of the silver vehicle. In this case, the proper response is to laterally brake, turning away from the silver vehicle until reaching a lateral velocity of 0 with respect to each other. The situation is now resolved, and the AV continues to intelligently use RSS to safely negotiate the upcoming merge. In this example, we see how the AV exercises caution around occluded areas. Let's take a closer look at how RSS rule number 4 works. Be cautious in areas with limited visibility. Here, as the AV approaches the crosswalk, there's a parked van occluding the AV's view of the sidewalk. Here we apply RSS rule number 4, which states that the AV should assume that there may be a pedestrian behind the occlusion. In other words, the van might be blocking our view of a pedestrian entering the crosswalk. Because of rule number 4, the AV begins decelerating even though there is no pedestrian in sight. Reasonable worst-case assumptions for pedestrians at a crosswalk are 2 kilometers per hour for their maximum speed and 2 meters per second squared for their maximum acceleration. The AV begins decelerating accordingly. After the AV does in fact detect a pedestrian, it continues to decelerate until coming to a full stop in order to give way to the pedestrian. Had the AV not made this assumption on what might exist behind the occlusion, it might not have had enough time to decelerate once the pedestrian had come into view. Let's watch it again. Let's look at another example of RSS rule number 4 in action. At this intersection, the AV needs to account for potential traffic. A large black van stops partway through the intersection, occluding the AV's view. Under rule number 4, the AV must proceed with caution until it can determine whether the way is clear. With its line of sight compromised, the AV must make reasonable worst-case assumptions for what might be on the other side of the occlusion. In this case, the AV accounts for 2 possible vehicles, one traveling straight across the intersection and another making a left turn around the AV. For each, the AV assumes the reasonable worst-case speed for this particular road at which the occluded vehicle might be traveling and the maneuver it will perform. Reasonable worst-case assumptions for the vehicle continuing straight across the intersection are 27 kilometers per hour for their maximum speed. For the turning vehicle, the maximum speed is assumed to be 18 kilometers per hour. The AV uses these assumptions to calculate safe distances with respect to potentially occluded vehicles. Applying rule number 4, the AV cautiously inches into the intersection, updating its assumptions about potentially occluded vehicles until its line of sight to oncoming cross-traffic is open. The AV also applies rule number 3 to determine right-of-way and calculates the safe following distances to the assumed occluded vehicles. Once it sees the way is clear, the AV completes the turn and accelerates to the appropriate speed. Had the AV not made these reasonable assumptions and a vehicle had emerged from behind the occlusion, a collision might have ensued. Let's watch it again. In the following scenario, we will look at rule number 5. If you can avoid a crash without causing another one, you must. This rule rarely needs to be applied because RSS already directs the AV to maintain a safety envelope in order to avoid potentially dangerous situations before they occur. However, sometimes other road users behave recklessly, and our AV must react accordingly. In this situation, the AV is driving on a multi-lane high-speed highway with other vehicles. RSS has determined a safe following distance between the AV and the vehicle in the middle. Suddenly and unexpectedly, the driver of the vehicle up front applies hard braking and decelerates rapidly. Having failed to take notice with enough distance to brake, the driver of the middle car swerves to avoid the decelerating car in front, moving over laterally into the passing lane to the left. RSS instantly calculates that while the new following distance to the car in front has increased, the longitudinal distance required to decelerate is greater than the distance remaining between the AV and the decelerating vehicle immediately in front. RSS therefore determines that the proper response is for the AV to perform an evasive maneuver, moving laterally into an adjacent lane to avoid the decelerating car. In this situation, even though it was the other vehicle's maneuvers that posed the danger, applying rule number 5 allowed our AV to avoid collision and restore its safety envelope. In this video, we've seen how the 5 rules of RSS were able to help an AV safely navigate in even the most complex driving environments. The secret is the AV's ability to make reasonable and foreseeable assumptions, allowing it to travel not only safely, but usefully. The formal proofs for RSS have been published for all to see. Not only is RSS sufficiently verifiable, the model is free of contradictions and supports all driving scenarios, meaning that if all road users were to implement RSS, there should never be any accidents resulting from failure in decision-making. At Mobileye, we understand that bringing AVs to the world's roads will be incredibly beneficial, but we'll have to work together across the industry and with regulators in order to overcome public skepticism. The RSS model was first introduced in 2017 to the academic world, and since then, hundreds of researchers from around the world have published dozens of papers further exploring these concepts, which ultimately led to the creation of IEEE 2846, the world's first standard that provides a framework for industry and government to come together to align on what it means for a machine to drive safely. Intel and Mobileye are honored to be leading this standard with some of the biggest players in the space, and we welcome others to join us on this journey to bring safe and scalable AVs to a neighborhood near you.